Handing over now to Trevor Hartnett, who's going to tell you all about the wonderful world of instrumentation for engineering of accelerators. Thank you. Over to you, Trevor.
Right, good afternoon. My name's Trevor Hartnett. I work at I'm a senior electrical engineer in the electrical engineering department at technology at Daresbury. And I'm going to talk you through a number of different projects that I've been involved with and how instrumentation has helped me complete these tasks. And you'll see that really these tasks aren't possible without modern instrumentation and techniques. So the first project I'd like to talk about is a project that we got involved with a number of years ago now. It's the earth stick test facility. So the first question you probably have is, what is an earth stick? So just there and those big things there are what people call earth sticks. We use them for as a safety measure for discharging potentially live high voltage equipment, so anything that could store any reasonable amount of energy, and reasonable anything bigger than about 4 joules really. We use an earth stick to go in and make sure that all of the components are no longer charged when we need to work on them. So this company, HVR, they are based up in Jarrow, near Newcastle, and they make high voltage resistors for a number of different applications, but they started this sort of spin-off of developing these high voltage discharge sticks, and they approached us to discuss verification of the operation of the sticks, which we thought, well, we can definitely have a go at this. So we had a look at it, and we had a look through the literature that was available, and we found that there isn't a standard for testing these earth sticks. So that was a big problem for us. So we had a look, and the closest standard we could find is this IEC 61010, and it's used for the verification of handheld probes for high voltage measurement. So we had a look at that, and mostly it's about making sure that the stick is in good, that the probe is in good condition, that that there's no breaks, that there's a good contact to ground, that there's this sufficient probe surface area, that the fault current that you get when you use the stick is not excessive and will not cause damage to the stick. So we had a look at those, and we wrapped them up in a standard a standardized test procedure that we wrote for ourselves. So what's in this standardized test procedure? So we perform a visual inspection of the stick to make sure that there's no apparent breaks or rips or anything like that in the stick. We perform a measurement of the resistor, the resistance of the resistor. And in most cases it's sort of tens of ohms up to maybe hundreds of ohms. This is so that when you do use the stick, and you use the stick in anger, that you don't get a massive fault current, as referred to if you just stuck an earth straight on a charge capacitor. You're going to get many thousands of amps possibly travelling through that earth. So we use a resistor to restrict that current. Then we do a high current continuity test to establish that the cable is able to take the fault current, or take the full current, and that the resistance per meter of the cable conforms with the manufacturer's test or expected values. Then we do a high voltage dielectric test, which is really starting to get into how the stick would be used. So normally these tests take place about 10 kV, but with a very low current power supply. And then we do the real beefy test, which is the discharge test. So we discharge the rated energy into the resistor, and we measure the temperature rise on the resistor. And then after we've done those discharge tests, however many discharge tests have been specified, then we do a final resistance check to make sure that the resistor hasn't been damaged by the tests, and that's the end of the test. So it sounds quite straightforward, but it's probably a little bit more involved. So up here I've shown us the sort of rating plate that you usually get on these earth sticks. So the resistance value, this one happens to be 600 ohms, peak impulse voltage 3 kV, but the maximum energy per discharge operation is a massive 62.5 kilojoules. Now 62.5 kilojoules is quite difficult to get into a stick at 3 kV, so with discussion with HVR, then we tend to put the energy in at much higher voltages, so we really stress the stick. Then they provide us with some clever calculations which give us the expected temperature rise on the ceramic of the disc, and we measure that and make sure that we conform, and then we allow it to cool for 15 minutes, and then we give it another 62.5 kilojoule shot. So this really stresses the stick, and I shall show you some test data that we've been able to get from these numerous tests that we've done now. So back in when we first started this project, we used a Tektronix oscilloscope. It's not a bad scope, isolated inputs. However, you're connected directly to the voltage probe, and we had sort of relatively low radiated emission from the system, but conducted emissions were travelling along, the cable from the probe, going straight into the Tektronix oscilloscope, and most of the time we got nice traces like this. Sometimes we got traces that just went straight up and flatlined, and basically the Tektronix, the electronics inside the scope had completely been hit by the electric field, and had stopped the scope from working. So this was a bit of a problem. So we changed the scope that we're using to a very cheap picoscope. It's not a bad little scope, low cost. You can link it directly to your laptop, and you get these nice plots plotted straight on your laptop, which is great. It seemed to perform slightly better in the radiated emissions that we were getting from the Earthstick test facility. Well, we then utilised galvanic isolation, so you can get them for about 20 quid, little fibre optic to USB interfaces. You can plug those straight in, so you can plug the picoscope into your fibre optic, you can run your fibre optic back to your laptop and then go back into USB, take it straight in, run the same software. The software doesn't know any different, so that worked really well, gave us nice galvanic isolation. You can see on the old traces we got a bit peaky right at the impulse. Here we've massively reduced that sort of peaky behaviour, so we were quite pleased with that. But the problem with the picoscope is that you do a shot and then you run over and you take your data off of the pico logger, and then you run back by the time the capacitor's charged back up again and discharge again. So you're doing it's not very automated. So we decided to address this issue. So the original system, low level of automation, low rate of energy transfer. You can see it here. So on this stick, we had to do two consecutive shots to get the required energy into the stick. This is the temperature rise on the stick. So we charge up, 30 seconds later we charge up again, and we hit the stick with the two hits. And then a short time, 10 minutes later after cooling, we hit it again. That was quite slow and cumbersome. So we've now upgraded to a solid state switch, much faster. We can now hit the stick with much smaller impulses, but over a very quick succession. So you still, if you look very closely, you'd still get these sort of peaky rises, but the temperature looks pretty much constant and just rises straight up like that. So, but in order to use the solid state switch, it's not much good me running backwards and forwards with this thing charging up at a frequency of about 10 hertz or something like that. So we used a National Instruments DAQ to provide higher automation and faster data acquisition. We're still ironing out a few of the issues. Trying to get the data out of this DAQ is a bit cumbersome because we actually get something like 45 million data points. So we have to strip back the data and sort of show much less data points. We don't need the full 42 million data points. So that's where we are with the system at the moment, and that's where the instrumentation has allowed us to move to. So the next area of instrumentation that I'd like to go on to is superconducting magnets. We've had a lot of experience with these over the last sort of 5 or 6 years on the mice experiment. So the mice experiment is a muon cooling and ionisation experiment, and it utilises superconducting magnets with their nice strong fields to interact with the very weakly interacting muons. So that's great, get all these superconducting magnets in, fantastic. What do we need to run superconducting magnets? A lot more than we do to run conventional magnets. So, because we're obviously cooled to cryogenic temperatures, we need to monitor the temperatures. Now, they're measured in these Lakeshore devices here. There's about 20 odd temperature sensors on each one of the magnets. They tend to be a variety of Cernoxes and Cernox resistors and silicon diodes. So we've got to use all this instrumentation to measure that. Then we also need to measure keep an eye on the pressure of the helium inside the vessel. That's handled just through some quite straightforward controllers down here. The only interesting thing about these controllers is they give us a pulsed output, so we can actually control the pressure within the magnet. We utilise a heater to do that. And then we also want to keep an eye on the liquid helium levels to make sure that the magnet is in enough helium. So we use these AMI 135 units to keep an eye on the helium levels. And then I've put voltages there. Now this is the big one. Those of you who've got experience of superconducting magnets, you know that there's expected number of training quenches, and obviously there's still the potential that it will quench when it's completed its training. Quenches are basically, for those that don't know, little warm spots within the superconducting material. When you're chucking 200-300 amps through it, they can quickly get very warm because obviously these strands are sort of much thinner than your hair. So putting 300 amps through a warm spot there will quickly warm up the magnet. What can happen then is that very large voltages can be generated because the inductance is still the inductance, unfortunately, and you can really damage the magnet. So our first sort of experience of quench detectors was looking at the decay solenoids, which is one of the first magnets in the cooling channel. It's where the pions decay into muons, if you're interested. We got given this magnet by PSI in Switzerland, and they developed this very nice quench detector. It's probably about 30 years old now, and we were worrying about the integrity of the system. But you can see it's beautifully designed. You can see all the nice copper tracks here on the detector cards. lovely isolation amplifier, which they had to get specially made for this particular application. This isolation amplifier provides galvanic isolation between the quench detector and the magnet itself, so that when the magnet does quench, because it will quench, the quench detector doesn't stop that, it means that the voltages on this side can come up to about 1,000 volts, but the voltages on this side will stay sort of below 10 volts. So this isolation amplifier is working quite hard. But we were worried about the integrity of the system, so I developed a modular system here, which has worked successfully for the last probably 3 or 4 years now. I updated all the components, new isolation amplifiers, all new amplifier circuits, much more modern manufacturing techniques. I wrapped it up in this nice EMC crate, which isn't very EMC in that picture because there's a big gaping hole there, but we filled that in, and we managed to get a very reliable, very robust system. The power supply and interface unit is down here that handles all of the communications between us and the quench detector, the control system and the quench detector. So we like this system. It works quite well. The voltage taps, 3 voltages come in. They're compared. They're essentially booked. That book signal is handed to an amplifier. That amplified signal has got a gain of about 270. Basically, the changes in voltage that you're looking for that signify a quench starting are sort of maybe 10 to 20 millivolts. So you've got to amplify them quite a lot really to get them up to a level that you want to work with away from the noise floor. So this isolated signal was handed over to an isolation amplifier. It's an AD210 for anyone who's interested. Then we go to a window comparator, which basically, if the signal is outside of a certain range, in this case it's about 4.5 volts, then it will de-energize these relays. Once these relays are de-energized, that's essentially the start of a quench being detected. That then carries on to open up contactors that separate the power supply from the magnet. So that we're taking away the power source from the magnet. The magnet is then allowed to discharge its energy through a dump resistor, and the whole process from quench to detection and open those contactors takes about 100 milliseconds, and then the whole process of the magnet dumping its energy into the magnet is in the order of about maybe 20 or 30 seconds. So once we'd finished with the decay solenoid, we then implemented this system on the focus coil, another magnet in the cooling channel. Again, it worked very well. However, this highlighted a requirement for a data logger. We utilised a National Instruments Compact Rio data logger, which worked really well. It's got 10 volts, 0 to 10 volts input, but it can actually take up to 60 volts going into it. However, this wasn't quite enough for obviously putting it on a magnet that can come up to maybe 600 volts. So what we did was we installed a potential divider to keep the voltages down. The reason we didn't use an isolation amplifier is because we wanted a true reflection of exactly what the signals were doing. An isolation amplifier, most of the isolation amplifiers that we could have used have got a slew rate associated with them, and they actually perform a little bit of filtering by themselves. Right, and so we we didn't utilise one for this particular activity. So that's the interface that we had for the Compact Rio. You can put in the number of channels that you've got, you can capture your trigger, and you can also set your capture time. So you can actually sample up to 10 kilohertz with this system. So we're really pleased with that one. So for the last 5 minutes, I just wanted to talk to you about the Eli MP project that we're working on, and we're using a lot of instrumentation to collect data on this system. Eli is an extreme light infrastructure for nuclear physics. It's a linear accelerator which produces high intensity gamma beams. They're tunable, these gamma beams. SCFC won a €5.5 million contract to build 21 accelerator modules, and the magnet power supplies and vacuum equipment that was required for these. You can see those racks here. So we've done a lot of testing on this system because it's for an external customer. It's not normal for us to do this level of testing, but you can see here that the stability of the power supplies is very good. We've utilised sort of DCCCTs to give us these signals, as well as temperature monitoring. So we normalise these stability settings to give us this 27 ppm value here, which you can see, which is very good performance for these power supplies. So we went on to measure the efficiency of mains interruptions, because this project is going over to Romania to be built, and we use a mains interrupter to interrupt the power going to the power supplies, and we actually dropped the supply voltage all the way down to 0 for 100 milliseconds with no ill effect. So the customer was very happy with these. So I think I'm running a bit short of time, but just going on to power quality here. On the MICE project, we use a power quality measurement system, another item of instrumentation. This generates reports on voltage dips, and we tabulate all of the results here. And you can see the sort of drops that we've had over the last sort of 12 months. This is an ITIC graph, which is a graph that's generated by the ITIC to say how devices should carry on working if the main supply is dropped by 0 to 0% for 10 milliseconds, and then obviously 70% for the next sort of just short of a second, and then should be able to cope with 80% drop for up to 10 seconds and a 90% drop continuously. All of our devices do conform to this. However, you can see here that there was 3 little dropouts, which actually caused interruption to the experiment. Instead of chasing our tails, wondering why various pieces of equipment had stopped, we were able to go to this graph and say, oh, look, there's 3 occasions here where we lost the mains voltage, and attribute the faults to those. So, sorry to rush through that last couple of slides, but if there's any questions, we might have time to take them.
Yeah, we've got time for a quick question. If anyone's got a question for Trevor. Oh, yes.
With your earth discharge sticks, what was the highest voltage you went up to?
In testing them, the system can go up to about 30 kV.
Okay. So what would that equate to in terms of an operating system voltage that you'd work with?
In terms of an energy?
Yeah.
So you can play around with the voltage and current to give you the number of pulses to get the energy that you want into it, but modulators and equivalent systems that we've got at DL It's all sort of pulsed applications. So, I mean, most of the sticks that we've only got up to maybe sort of 60 or 70 kilojoules as a stored energy. So.
Okay, well.
So that's just really a follow-on question to that. At 30 kV, what sort of solid-state switch were you using to test the HVR sticks?
We used a thyristor.
Single Forester?
Pardon? A
single Forester?
No. It was from our friends over in New York, APP. They've started making arrays of thyristors. The one that we use on this system there's about 8 thyristors, and it's optically triggered. And it comes in a little moulded box, and you just give it an optical trigger and it fires. It's great. The only problem is that the I squared T value is about 9,000. So you need we had to install a resistor to keep the current, the I squared T value down.
Okay, that's about all we have time for, so let's thank Trevor.
Thanks very much.
Thanks very much.